Hi, my name is Thiago, and this is the presentation for the final project for the constrained robotic control subject, entitled Drone Show, the use of control barrier functions and guided vector fields for drone control and dynamic obstacle avoidance. We first are going to talk about two abstractions done in the work, then we're going to talk about path planning, guided vector fields, obstacle avoidance using control barrier functions, and then the final result is going to be shown. The first abstraction is regarding drone localization. It is always known. We know that in real life we would get this from sensors, but this would add an extra layer of complexity to this work, and since we want to focus on control barrier functions, this is taken as granted. Static obstacles are known, and also the parameters such as position, velocity, and acceleration for dynamic obstacles are known. The second abstraction is regarding drone dynamics. We know that drones can be pretty complex, so their dynamics is somewhat abstracted here. We consider a perfect low-level controller with no delays or perturbations, and also no external disturbances. Orientation here is also not relevant, as drones are considered a luminous point in space. For the path planning, we first define a master point, a normal unit vector, and a phase angle in a way that we can calculate all of the drone's relative positions and then create a final path. So first we define the central point and the formations such as a circle. Then we define a normal vector, which then defines the plane in which the drones are going to lie, and then a phase angle, which allows us to rotate the drones around the normal unit vector. The show has 5 phases, the first one being the drones leaving their initial positions and reaching the first point. The second one, they're going to create a circle around the positive z-axis, and then they're going to move back and forth in x while rotating around it as well. They're going to rotate around z and then move back and forth along y while also rotating around it. Now we're going to talk about trajectory problems, and that's because they impose a time constraint, which means the drones must be at state q at time t. And that, especially in highly dynamic systems, can be a problem and can be dangerous because this can generate a very large control action if there is a delay, for example. And also, we're not guaranteed to go through each point if we have a delay, for example. The drone will simply try to go as fast as it can to the desired position. Since we're talking about a drone show, going through every single point is actually an essential part of the task. For that, we use guided vector fields. So given a parameterized curve P, we can define a velocity for each point q in space in a way that we define a normal and a tangent component to the curve. The farther we are from the curve, the greater n has to be, so we converge to it, and then as soon as we are close to the curve, the tangent component allows us to circulate on the curve P. We then do a weighted sum using g and h, as we saw here, and in order to understand how these values are calculated, we have to look at the work of both Vinicius in 2010 and Adriano in 2021, entitled respectively Vector Field for Robot Navigation Along Time-Varying Curves in N Dimensions and Constructive Time-Varying Vector Fields for Robot Navigation. One paper that has been published using exactly this idea and this algorithm is entitled Autonomous Navigation System for a Delivery Drone, which I am one of the co-authors. Now let's talk about control barrier functions, which are both a technique to reinforce constraints in a control loop and also a class of functions that play a fundamental role in this technique. The first idea is that given a constraint, we can define a differentiable function b of q, which is always greater than or equal to 0. And the central idea number 2 is that if we can guarantee that dB dt, not q, but dB dt is also greater than or equal to minus eta b, eta greater than 0, the constraint is always respected, as we're going to see here for first order kinematic control. For first order kinematic control, of course, the input is q dot, which is the velocity, and since we want to enforce the constraint b of q greater than equal to 0, as we saw before, if the time derivative is always greater than or equal to minus eta b, we can prove that if b0, which is the barrier function b at time t0, is greater than 0, then b of q will always be greater than 0 as well as t goes to infinity, because this term, this exponential decay term, appears. And then for this kinematic control problem, we can define this minimization problem seen here, subject to this constraint here, dB dq times u greater than or equal to minus eta b for any number of constraints that we want. But now, B doesn't depend directly on T, which is what we want. We want dynamic obstacles, which are moving in time. So if we were using first order kinematic control for a B that depends on time, we can see that after differentiating it with respect to time, a new term shows up here, which is a feed-forward term. And similar to what we saw before, we have the same barrier function, but with this added term here. Now, since we are controlling drones and we're using second order kinematic control, so we are controlling acceleration, we have a different setup here. So we still want to make sure that the barrier function is always greater than or equal to 0. But if we use the first order CBF, the control input, which is acceleration, is not going to appear. So since we don't control velocity directly, which is the term that shows up here, we have to differentiate this with respect to time once again and get to this expression here. Once again, it is proven that if b0 is greater than 0, this whole expression is going to be greater than 0 as time t grows to infinity. So for a second order kinematic control, the optimization problem becomes bigger, as we saw here. And also, the barrier function becomes of this type, dB dq times u. Now u is the acceleration, of course, is greater than or equal to this whole expression here on the right. But again, B doesn't depend on time, and since we're dealing with obstacles that are moving in unpredicted ways, B has to depend on time. So as we compare time invariant TBFs and time variant TBFs, we see that now B depends on time, and as we take the first derivative, we see that a new term shows up, and also as we take the second derivative of B, since it depends on time, we see this whole new expression here. So now we see that dB dq times u is greater than or equal to this expression here, where the parenthesis here is b dot, as we see here, and then we have minus eta squared b minus all these terms that show up as soon as we take the second derivative with respect to time of b. So then if we compare time invariant and time variant TBFs, we can see that we have something of the type dB dq times u greater than or equal to this whole expression here on the right, which is a lowercase b, if we consider this a linear equation, such as a u greater than or equal to lowercase b. As we look on the right, we see that now we have all these expressions here, all these terms here, which again come from this derivative. Now I'm going to show the results. I have the simulation open here. So we have three large obstacles here, dynamic obstacles. We have the drones in a random position, as we see from the blue dots. We have static obstacles, such as the purple cubes, the grid, and also the barriers here on inside this box. So as the drones try to reach the first master point here in the center, they are also avoiding all the obstacles. So again, the position, acceleration, and velocity of all obstacles are known. So you see that the drones are already trying to avoid them. So they're going to the second point in the formation while also avoiding all the dynamic obstacles. So they create this complex formation to try and avoid all the moving obstacles. So now I'm going to accelerate the animation just a bit, just so we can see that the drones are able to perform the show while also avoiding all the obstacles. So now as we move this a bit faster, we can see that the drones are constantly avoiding the obstacles. If they get close, the drones spread out or do whatever maneuver they have to do in order to avoid all three at the same time. You see that in some cases it gets pretty complex because all the obstacles are moving exactly where the drones are, so they have to do some pretty complex maneuvers. So again, we don't consider any disturbances in the environment, so that's why we see their movement like this. So let me go through the show again. They're going to move back here in X while also avoiding all the obstacles. Then they're going to turn in Z 90 degrees while avoiding the obstacles. You can see how they really create a barrier and in a way that the drones have to avoid them. And this is the final part of the presentation. where the drones reach the final formation. So that's it. If you have any questions, please let me know. I'm available at my email, which is shown on the screen. Thank you.